Hi all. So today we are going to see the topic Pushdown Automata. This is the section 21 in our Automata theory and formal languages. Okay, I am Dr. Sunita from CSE department of KLU University. Now the aim of our section is to provide the understanding of Pushdown Automata, their structure, working principles and their applications in the field of theoretical computer science. And these are the instructional objectives and the learning objectives, learning outcomes. Okay, so Pushdown Automata is something related to context-free languages. Okay, so when we talk about context-free languages, it can be represented using context-free grammar and Pushdown Automata. And Pushdown Automata is nothing but it is an automaton attached with a memory content, that is stack. Okay, when we talk about finite automata, there is no memory in finite automata, but when we come to Pushdown Automata, we have a memory and the stack is used as the memory here. So it is working in the mode of first in last out principle. Then this is the architecture for Pushdown Automata, where we have the input is stored in the input tape and the machine has different states and transitions, and there is an attached stack. Okay, so when we consider the stack, here we are using a special symbol, either $sign or Z, to show that this is the end of our stack or this is the bottom of our stack, or in the middle of our processing, if we find a dollar or Z, that means that we have reached the end of the stack or the stack is empty. That is the speciality of the symbol. Then transitions, when we mark transitions in PDA, we have to label every transition with the 3 data. The first data here, it is A, that is representing the input symbol. What is the current input symbol to the machine? Then the next symbol is B, arrow C. Okay, so B means that is the element on top of the stack. Okay, that will be popped out, and after arrow we have C, so that is the third symbol. That means that C will be pushed to the stack, or in effect we can say that the element B on stack top, that will be replaced with the letter C. So that these are the 3 elements we have to label on every transition in a PDA. So what is the input symbol, what is the stack top, and what is the element to be replaced with the stack top. And instead of this arrow, we can use this slash symbol as well. Different textbooks follow different methods. So we are going to follow this arrow symbol. Then so consider the transition Q1 to Q2, where A, B arrow C. That is the transition we have. That means if the input is A and if the stack top is B, that has to be replaced with C. That is the thing. So see, in the input tape we have A as the input symbol. Next input symbol we are going to process is A, and the current status is like this. On top of the stack we have B. So the transition says that if you have the input A and the stack top is B, the machine has to change to the state Q2, and at the same time this B has to be replaced with the C. Okay, so the state the B is now going to replace with the C. Okay, after processing A, that is what happening here. So B will be replaced with the C. B is popped out and C is pushed in. So in effect B is replaced with C. Then another kind of transition is, instead of this B we are representing epsilon or lambda. That means the epsilon value, null value. So this means that we are not popping out anything from the stack, instead we are pushing an element. That is, there is no pop operation. Whatever there on the stack top, we are not bothering, we are simply pushing the element, the third element that is specified here, it is C. That will be pushed to the stack, that is what. Okay, so we can see that here some elements on top of the stack, we are not bothering what it is, but we are going to simply push C on over to the stack. That means without popping out B, we are pushing C. So this transition, this kind of transition represents only the pushing operation, not it does not have any pop operation. And the reverse is also possible. That means we can just pop out some element from the stack without pushing anything into it. So this A comma B arrow lambda or epsilon means if the input is A and the stack top is B, just push it out, just pop that value from the stack, no need to push anything. So that is the thing. So we have B on top of the stack. So after this transition, that P is popped out. Now the current stack top is H, that is the next element. So these three kind of transitions are possible, and one more is there, that is both push and pop operations are not there. We are not making any change to the stack content, we are just taking a state change. So from Q1 to Q2 there is a state change on input A. There is no pushing or no popping operation over here. So see, the stack is here BHE, these are the contents, and after transition also BHE remains there because we are not popping out anything and we are not pushing anything into the stack. So these are the different kinds of transitions possible with the PDA. So replacing the top element with something else, or simply pushing into the data, into the structure, into the stack, or just popping out the element from the stack, or does not make any change to the stack. All the four kind of transitions we can do. Then this is another thing, when the stack is empty, dollar means the empty stack. So if the stack is empty, we can just pop it out and the stack will be totally empty. That is another possibility. And in some cases there may not be any transition. So we have defined a transition like Q1 to Q2, input A, and the stack top is B, that has to be replaced with a C. Okay, but when we check the stack is totally empty. There is no symbol called B on top of the stack. So this transition cannot be taken here because the conditions are not satisfied. At this condition, what happens? The machine will halt at that position at Q1 and it will reject the current string that it is processing. Okay, that is a rejectance condition. Then no transition is allowed to be followed when the stack is empty. So the empty stack we cannot work with. Then this is a good transition because we are replacing that last symbol with the symbol B. That is can be there. Then non-determinism in PDA, which is called NPDA, that is non-deterministic PDA. That means for one input we can have multiple transitions. So for example, here from Q1 there are two transitions for the input EA. Either it can transit to Q2 or it can transit to Q3. So that is multiple transitions possible for one input. That is non-determinism. Then epsilon transition is also allowed in the non-deterministic PDA. So we take some transition or push and pop operation on the stack without input as well. Then this is one example for a non-deterministic PDA which has 4 states. Okay, some transitions we have labeled. We can see this is with a sample input value. So suppose this is the input, A, B, B, B is the input. Okay, how the machine is going to process this string, whether it will be accepted or rejected by our PDA, that we can check. So initially the machine is in Q0. Okay, that is the initial state. And there is a lambda transition, so without any input we are going to take a transition to Q1. Okay, so now the machine is in Q1 and the input we are going to process here is A. Okay, so the first input is A. So what this transition says means if the input is A, then we are not popping out anything from the stack, we are simply pushing that A to the stack. So what happens here? The stack is filled with one A. So whatever A we read, we are going to push into the stack. Okay, now we are going to read the next A. So again we are in the same state Q1 and the same transition will be taken, that is that A will be pushed to the stack. So you can see A is there, second A comes to the stack. Then we are going to see the take the next A. Again the same transition will be taken, that A will be pushed to the stack. So far we have read 3 A's and all the 3 A's are on the stack right now. Then we read B. So when we get the input as B, what happens? We have to take this transition to Q2. So the current state is Q2. And what this transition says, whenever we find B, if the stack top is A, we have to pop it out. We need not push anything again. we are popping out A. So whenever we find A, B, so we have to pop one A from the stack. So this A has been popped out. Then the next element we read, that is also B. So what happens, this transition will be taken, this self loop. So when we find B, we have to pop out one A from the stack top. So that second A also popped out. Then we read the next B. Again the same self loop we are going to take, same transition. The remaining A will be popped out from the stack. Okay, so now the stack is empty and we have reached the end of the string. So we are at epsilon, we are reached the end of the string, and the dollar is there on stack top. Then we will move to the final state of our machine Q3. And once we reach the final state and the input string is over and the stack is empty, when these three condition occurs, we accept the current string. So the current string is A, B, B, B. So that is accepted by our machine. So what is the acceptance condition? A string is accepted if there is a computation such that all input is consumed. All the symbols in the string should be consumed. And the last state is a final state. We must have reached the final state after consuming all the input, and the stack should be empty. That is the condition. So this is the input we have given, and this machine accepted the string. So what will be the language accepted by this PDA? So this is the language accepted by our PDA, A raised to n, B raised to n. That means equal number of A's and equal number of B's should be there in the string. So this is one example. Then another example, this is with the three states, Q0, Q1, Q2, and some transitions are there with the epsilon transition as well. So this is the PDA for even palindrome. WWR means it represents the even palindrome strings, palindromes with the even length. Okay, let us take an example, A, B, B, A. So it has length 4, it's an even palindrome. So how it is going to be processed? So initially we are at Q0 and the input symbol is A. So we read this A, this transition will be taken, A will be pushed to the stack. Then we read B, so what is for B? If we find B, B should also be pushed to the stack. So we assume that we have reached the middle of the string, then we will move to the next state Q1. And what Q1 is going to process, if we find a B in the input, and if the stack top is also B, we have to pop it out. So that will happen. On top of the stack we have B and the next input symbol is also B. Okay, in both places we have B, so we pop it out. Then next we read A. So if we find A, the stack top should be A, then we will pop it out. Okay, that is all. Then we reach the end of the string. So at that time what happened? The stack is empty. So we will move to the final state Q2 and the string is accepted. So ABBA is a palindrome and it is accepted by our machine. Then we consider another rejection condition, a negative example we can take A, B, B, B. So we know that this is not a palindrome. So this string should be rejected by our machine. So we can see, start with the Q0. So in Q0 we are going to read A. So A means we have to push to the stack. Then we read B, that will also be pushed to the stack. And we assume that we have reached the middle of the string and we will move to the state Q1. And what happened in Q1, we are reading next to B, we are going to check whether B and on stack top also B. Then we will pop that B. So the stack is remaining A, stack is having A. And we have another B over here on the input, and there is no transition defined for input B and stack top as A. Okay, input is B, we are expecting stack top as B. If any other condition comes, the machine cannot process it. That means that the machine will halt at Q1 and it will reject the current string. That is A, B, B, B will be rejected by our machine by halting at Q1. That is the case. Okay. So there is no computation that accepts the string ABB. So ABB is not belonging to the language and that is rejected. So a string is rejected if there is no computation such that all input is consumed and last state is a final state. Okay, that condition is not happen here, so it is rejected. In other words, a string is rejected if in every computation with the string the input cannot be consumed, or the input is consumed and the last state is not the final state, or the stack head moves below the bottom of the stack. If any of these three happens, the string will be rejected. Okay, then another possibility is instead of pushing a single symbol, we can push a string into the stack. So here A comma B arrow W means if the input is A and the stack top is B, we can push the string W. Okay, more than one string, one symbols we can push at the same time. So this is the case. So A comma B arrow CDF means B will be replaced with the C, D and F. Okay, so on stack top we had B and it was replaced with the C, D, F. So see the order, C comes at the top and D, F. Okay, like that. So instead of one symbol, we can deal with the multiple symbols or the string. So this is an example for this, that is we have to accept all the strings which have equal number of A and equal number of B's. Okay, if there are 5 A in our string, 5 B should be there, but it can be in any order. That is the. So this is the machine that accepted that kind of strings. Okay, so we can take this example A, B, B, A, B. So both these number of A is 3 and number of B is also 3. So this must be accepted by our machine. Okay, so first we are going to process A. Stack is empty and the machine is in Q1. Okay, so we are going to process A. So when we find A, we are going to push 0 to the stack. And when we find B, then also we are going to we are going to pop out that 0. Then when we find the next B and the stack is empty, we are going to push 1 to the stack. Then B comes, again B comes means we will push 1 to the stack again. So now it is 1 1. Then we read A. Then we will pop out 1 from the stack. When we read 1A, that 1 will be popped out. Then again 1A means again 1 will be popped out. Okay. Then the stack is, we have completed all the strings, all the characters in the string, and the stack is empty. We will move to the final state. That means the string is accepted. Okay. That is the case. Then the definitions and formalities of NPDA. Okay, so this is the transition function. Delta is the transition function. Q1 A, B, A is the input string and B is the stack top. Then it will be, then Q2 will be the next state and the stack top will be W, that is the string. Then when we have the multiple transitions, we will write like this. So from to Q, next state could be Q2 or it could be Q3. So that will be written like this. Then the definition of NPDA is like this: M is equal to Q sigma gamma delta Q0 Z and F. Q is the set of states, sigma is the input symbol or alphabet, then tau is the stack alphabet, delta is the transition function, Q0 is the initial state and Z is the start symbol, F is the final state. Then this is the instantaneous description. Instantaneous description means we have to specify what is the current state of the machine, what is the remaining input to be processed, and what is the current status of our stack content. These three elements should be provided to specify the current status of any PDA. So that current status is called the instantaneous description. Okay, so we can start with this Q1 BB AB AAA dollar. That means Q1 is the current state of our machine and BBB is the remaining input to be processed and the stack content is AAA. Okay, so let us assume the input string was AAA BBB. So out of those, the first three characters we have already processed. That is why the second element is BBB only. Okay, now we are going to process the remaining. We have to start with the next B. So what will happen there? When we read this B, we will take this transition and we will pop out one A. Okay, so that the next state will be like this. Next instantaneous description will be this: Q2 BB AA. So the remaining input is BB and the stack element is AA. That is the thing. Then the next step we are going to process the next B, and it will go like that. Okay, so that will go like this, and every step we process, every consume one symbol from this input side, and will make appropriate changes on the stack. And if we finally reach on the final state, then the string will be accepted. That is the condition. Okay. This can be written like this: we start with the Q0 with an input W and the stack element is S. Okay, and after processing this W, if we reach the final state and we could consume all these elements in the string, means the second element will be lambda or epsilon, and stack must be empty sometimes. So this condition we will accept that string W. Okay, that is the case. So we can try with this example, we will get the answer. So that is all about the NPDA, and thank you for listening.